Euclidean geometry. So we just looked at Cartesian geometry. Of course, they're both geometries, and you can use Cartesian geometry sometimes to help you solve a Euclidean geometry problem, and sometimes you use Euclidean geometry ideas to solve Cartesian geometry problems. They all interact, it's all maths. Some definitions though, some things that are particular to geometry. So notation that we use, of course we have our two vertical lines, meaning is parallel to, our upside down T perpendicular to, three horizontal lines congruent to, three vertical lines similar to, three dots forming a triangle in thus format is therefore, and if it's the other way around, that stands for because. Oh, you didn't know that one. Yeah, I mean, so, because sometimes if you think about it, you're writing the reasons down. Some people like to state, oh, this is why, because, da-da-da-da. And so they use the upside down triangle. It's not used that often, but that's a notation you can use for because. So it's terminologies. We talked about this one the other day, didn't we? Produced. Produced in geometry means the line is extended. And the way we say it's important. So there's xy. I suppose it's more correct to say the interval is extended rather than the line is extended. But if we said xy is produced to a, then that's the direction we go. We go from x to y, we produce to a. If we wanted it the other way, then we'd say yx is produced, let's say, to b. So we'd start at y, we'd go to x, produce out to b. Foot means the base or the bottom, but strangely enough it doesn't actually mean it is at the bottom, because of course I could have a diagram like that, and even though B is sort of on the top of the picture, B would be the foot of the perpendicular. Collinear, well, we mentioned that in coordinate geometry, points that lie on the same line, and concurrent, lines that intersect at the same point. Transversal. We often see those in parallel line questions, but a transversal is simply a line that cuts two or more other lines. Some conventions in geometry. Whenever we name an angle or a polygon, we always do it in cyclic order. Now it doesn't matter whether you go clockwise or anti-clockwise, that's your choice, but it should be in order. So an angle like that I could call ABC. Now when you write angle, some people put the angle symbol out the front. That's probably the most common way of doing it. But another way of writing the angle is with the little, what do they call that, a caret above the B. So above whatever the vertex is. So ABC, that's a bit rarer. Of course, if there's no ambiguity, then I can just simply call it angle B. Okay? You only really have to name all three if it's ambiguous. What do I mean by that? Well, if you had a situation of vertically opposite angles and B was in the middle, there's four possible angles if you just said angle B, so you would name it. Whereas this one, whilst there is actually two angles there, because there's the acute angle that I've drawn in, and there's also the reflex, we always assume the acute or the obtuse. If they want the reflex, then they would write angle ABC reflex or something like that. This quadrilateral, so many different ways I could name it. I could call it VPQT, QPVT, QTVP, many others. In fact, there's a good permutations question. How many ways could I name? Anyway. Parallel lines. When you name them in corresponding order. So if I've got this situation, I would say AB is parallel to CD. Or I might say BA is parallel to DC. But I would not say AB is parallel to DC. Okay? So get them in the same direction that they're flowing. So keep them in the same order. Equal lines, as we know, we mark that with the same symbol, most commonly just a dash, or if we've got a quadrilateral, one side opposites might be equal, so one dash and two dashes on the other one. So that's telling me that PQ is equal to SR and PS is equal to QR. You've done a lot of geometry in the junior school, okay? You should know most of these theorems, you know, without me even telling you them. You've seen a lot of them. It's probably been drummed into you. And I guess what I'm more concerned about here is the setting out of the proof. How do we write down a good solid proof that someone can read and understand what you're doing? So when we're constructing our proofs, okay, you're going to write down lines in your proof, of course, but you can't just write anything down. You just don't pull things out of thin air. It should be, well, given information. Often there's information in the problem that's given to you. But don't assume it's given to you. And the example I've put there is a classic one. You might be told two sides of a triangle are equal. So you might have a triangle and they tell you AB is equal to AC. But they have not told you it's isosceles. You have to prove that's isosceles. Okay? So you can't just assume it's isosceles, because part of your proof would be, oh, okay, you've told me AB is equal to AC. That was given information. Therefore, this triangle is isosceles. And now I can use facts about isosceles triangles. You might construct some new lines or new points or things like that. So you should describe clearly how you constructed it. So a person could reproduce it on their own diagram if they wanted to. And of course the third thing is a recognised geometrical theorem or assumption. I say recognised there, as you can't just pull something out of thin air and hope for the best. Okay? So any theorem that you write down must be explicitly stated. Now how you state it, whether it's in your working out or whether it's in your reasoning, but it should be there. Now I'm real fussy on this. Here's an example of an angle sum of a triangle. A lot of people write things down like angle A equals 180 minus. No, that's not what the theorem states. The theorem does not state any angle in the triangle is equal to 180 minus the other two angles. That's not the theorem. The theorem is the three angles of a triangle add up to 180. So that's what I write down. That's what I mean by explicitly writing down the theorem. The three angles add together to give 180. The reason I do, well, angle sum of a triangle is 180. Notice in my reasoning there, acceptable abbreviations. So ones that we know. The angle symbol I've used for the word angle, that's fine. That's a recognised geometrical abbreviation. The triangle symbol. And of course, for that matter, I've used the equals symbol instead of writing the word equals as well. Okay. Any reasoning you put down needs to be clear and as concise as possible. So don't waffle on. It should be as concise as possible. Okay. And of course, the last thing that you might write down is anything that logically follows from other lines that you've written down. So it might be, oh, well, I've just added the numbers together from the line above or something like that. Okay, so our theorems. We'll probably start off with this old one. Okay. The angles in a straight line add up to 180 degrees. So let's say we wanted to work out x. Now if it's just a numerical problem worth one mark and they simply say find x, fine, I'll just write down x is 150. There it is. But if it's in a proof, then I would write this down. I'd say x plus 30 is 180. Now the reason I give is simply saying, well, ABC, I know that's a straight angle. But some people write down angles in a straight line. Some people write down adjacent supplementary angles. Have you ever seen that way? Good. Because if you have seen it that way, forget it. I hate that one. Alright? Because what happens is you get a problem where there's three angles that add up to 180 and they go, oh, supplementary angles. Well, that's impossible, because supplementary angles are defined as two angles that add up to be 180, not three angles that add up to be 180. So I'd steer clear from that one. Then I'll go and solve it. X is 150. Now, if I really, really wanted to be pedantic on this one, then there should have been an even earlier line than the x plus 30 equals 180, where I'd said, well, look, angle ABD plus angle DBC is equal to 180. But in this case, there's no ambiguity. there is only one angle labelled with x. There is only one angle labelled with 30, so it's clear which angles I'm talking about. But if you've got a diagram where there's a couple of angles marked 30, then you wouldn't put plus 30 because they say, well, hang on, which one are you using? Okay? So it becomes ambiguous. Vertically opposite angles. Vertically opposite angles are equal. No, you can't write vert op. Vert op is not an accepted abbreviation. Last time I checked, vert, anyone doing French? Or do you remember your French? Vert, I believe, is French for green. So you're talking about the green angles. The green op angles. Which ones are green? Mine are red. Alright. So in this one, I'd say, well, look, 3x equals 39. I can't actually name the angles in this one because they haven't given me any. And I would write vertically opposite, the whole thing, vertically opposite. But angles, again, I can use the angle symbol, and equals, I can use the equal symbol. Solve that, 13. Angles about a point, add up to 360. Now, the reason I always use for this one, well, let's do an example. Let's say they're all the angles that I've been given. I simply would say revolution. Same as back on the first one, I said, well, that's a straight angle. Well, that's a revolution angle. Right? So rather than writing angles about a point, it's quicker just to say, revolution. It's a revolution angle, that's 360. I know revolution is 360. And I get y is 75. Parallel line theorems. We have alternate angles. Now, I don't know how you were first shown to remember these things. Alternate, the z angles was how I was taught. So if you look at the angles, the ones that can form a z might be a backward z, but they would be the alternate angles. So we have two pairs of alternate angles. We've got C and F are alternate, and D and E are also alternate. If I was going to use the idea that they're equal, I would write, well, I'm talking about the alternate angles. And I know the alternate angles are equal, but there's actually two pieces to this proof. Parallel lines. Because you can have alternate angles on lines that are not parallel, they're just not equal. So it's the two things that make them equal. The fact that they're parallel and the fact that they're alternate. Where does the word actually come from? Well, if you say alternate a little bit differently, it might become obvious. Alternate. Yes. So you're comparing the two parallel lines, and they're alternating on either side of the transversal. And that's where that comes from. So one's on the left-hand side, one's on the right-hand side. Then you get corresponding angles, which they form an F. And there's actually four pairs of corresponding angles here. So A and E are corresponding, B and F is corresponding, C and G, and D and H. Why are they called corresponding? In geometry, corresponding means in the same position. Right? In the same position. So if you look at the two parallel lines again and you're comparing, the A and the E are in the same position. The B and the F are in the same position, and so on. So that's where the word corresponding comes from, and why they're called corresponding angles. That leaves us with co-interior. These are the ones that form a C. They're not equal. They're the ones that are supplementary, and that's a correct use of the word supplementary because we are saying two angles that add up to give 180. So C plus E would be 180. D plus F would be 180, and I don't actually use the word supplementary because I think it's quicker to write equals 180. So co-interior angles equal 180. Co-interior, again, co means the prefix co, together, interior, inside. So again, compare the two parallel lines. They are together on the inside of the parallel lines, as opposed to the alternating ones. So those are the ones that are together, co-interior. Let's try a problem then. It's not a particularly hard one, but it's one where we can do some of these things and for the setting out. So we've got x and y we have to find. I'd probably find x first, I think. So in this one, it's okay to write x plus 65. There is only one angle labelled x and one angle labelled 65, so there's no ambiguity there. They add together to give 180. Reason being, well look, the angle CQD is a straight angle, so I know that's going to equal 180. Solve that. Okay, I now know x is 115. Now to work out y, well, there's different ways I could do it. I'm going to construct a new line, xy, parallel to CD, that passes through P. So this is how I'll create it. So that if you have this diagram, you could go, oh right, you put it there. So xy, parallel to CD, passing through P. Now, angle XPQ would be the same as 65. Again, no ambiguity there because nothing else is identified as 65. So there's alternate angles. Now, I don't write parallel lines here because I have named the parallel lines. Plus, I've also got 3 sets of parallel lines. So I want to identify which ones I'm using. So XY is parallel to, well, I could call it CD or CQ. It doesn't really matter for this one. Now, XPB plus the 120, they're going to be 180. We've got our co-interior angles. So I know XPB is 60. Now that angle Y, which is angle BPQ, is the same as XPQ plus XPB. Now when I use that one, I say common angle. Because what I'm basically saying is, look, it's the same angle I'm talking about, I'm just describing it in 2 different ways. So it's a common angle, it's the same angle I'm talking about. Substitute in, and there's my answer, 125. Alright, so book 2, look, on those quick numerical ones, if they're not asking for a whole formal proof, it is okay just to go, oh well yeah, I'll work out x and it's this. But if it's a formal proof, then we should be putting our reasoning down and explaining. So it's more those multi-step ones where it's important.